in mind where yes, progress. Let's talk about progress. But let's just recall what we were where we stopped last time. So we had this kind of a left side and right side, and on the right side we were essentially doing kind of a Boltzmann perspective, namely saying out of multi-particle probability distribution. We're now talking about a single particle probability distribution. And generally, it depends on the probability of particle being in this point at z momentum, but we say that it's translational invariant, so eventually it's only about a single function of one momentum, and then we, by decoupling correlators, we wrote the Boltzmann equation, which essentially says that you need to integrate over dp1, dp1 prime, dp prime, and there is some probability, and what stands here is rho of p times rho of p prime minus rho of p1, rho of p1 prime, and there are delta functions which impose that energy of p plus energy of p prime minus energy of p1 minus energy of p1 prime is zero and the same about momentum. P1 minus P1 P prime. This was kind of the right side of it. There were like particles colliding. And then we had on the left side something kind of which looked very different, which was equation on the occupation number, which was, it doesn't look like a probability distribution. This is just a moment of amplitude, complex amplitude of the wave averaged over the short intervals, short windows of time. And for this moment, we wrote an equation which look like, again, integral of dk1, dk2, dk3, and there was some kind of a matrix element. And there was a combination which was k and 1 and 2 plus I won't try to remember there was delta function of omegas and delta function of k's, very much like here. If you say that your epsilon is h omega k, or is somehow related, and then we say that that's kind of look different. One is on probability distribution, another is on a moment. But then what we wrote in between, we wrote the equation, which was a quantum kinetic equation, which was just saying, okay, let's take this Hamiltonian from which we started here, which was omega k, a, k, a, k. We could read it and put it like this, make a symmetric version of it, add interaction which would look like A1, A2, A3, A4. And again, assuming that our interaction is very weak, we classify our field now, a quantum field, by a state of a free field, which is actually oscillators with frequency omega, which are characterized by their quantum numbers n. And then we wrote equation with this quantum number a, which was what is for a given k. For a given k, I have this omega k. So I have an oscillator and it has occupation number. This is its occupation numbers for a given k. Every is independent on every other. And what I wrote over here was, of course, the integral. And again, I had here in the first non-vanishing order n. And what I had something like nk plus n1 plus 1, n2, n3 minus n nk, what we had is nk plus 1, n1 plus 1, n2, n2, n3, minus the combination where we have nk, n1, n2 plus 1, n3 plus 1, and the delta functions are of omegas and and k's are all the same. And then what we say is that essentially, if we consider limit n much larger than unity, and we say that nk is just nk times a bar, so this is a dimensionless. Those are action. They are, because A is P plus IQ, they are symmetrized canonical variables made out of momentum and coordinates. So n's have dimensionality of action. N's are numbers, they are dimensionless. So when I take this and I assume that this is much larger than unity, so I neglect ones here, except so no, the terms which are fourth order in n cancel. So what would be remaining is the terms of a third order, which would give me this equation, and the terms of the second order I'll neglect because the occupation numbers are large. On the other hand, in the opposite limit, I can say that my n's are much less than unity, and here I'll take only quadratic terms, and then I'll get this equation. But now I would kind of interpret it as kind of n p's, or saying that k is p over h, so you see that formally this quantum kinetic equation bridges, and it tells you that you essentially can treat kind of this also as an occupation numbers in a sense. Okay, so now what I want to
intuitively it's kind of if you go to small numbers, it looks more stack math. Is that the
when you would go to small numbers, which means that your cubic terms are much smaller than your quadratic. That's essentially what you do here. Right? So when you look here, this is a general equation. It has fourth order terms, they cancel. So it has cubic and quadratic. Okay, so this is cubic, this is quadratic. Okay, which tells you that whatever you do at some ends, there's probably a natural counterpart of the other end. Okay, and this is the bridge. Okay, yes.
Can you remind where that equation comes from? Just
Yeah, so let me remind you where this equation comes from. We get it totally classically. Namely, we took this Hamiltonian, we wrote the equations of motion, which is just, it's a very simple symplectic structure, namely this just this equation of motion, which means that this is omega k a k plus well, sums it would be faster, lambda k 1 to 3 a1 a2 a3. So this is a nonlinear equation, but we are interested in its statistical properties. So one of the ways to treat it, as we discussed, there are several ways to treat it, and it's not clear to what extent they are equivalent. We spent a lot of time. But let me remind you one way. So you just add the random force here and random dissipation. In equilibrium, it's naturally your contact with the thermostat, and it imposes just equipartition on a classical field. But generally, you can treat it different, just like some functions. And then you just solve it perturbatively, because you're interested in the equation on this. So you multiply it by A complex conjugated, you add complex conjugated equation, this term would disappear. So you would essentially have, well, essentially you can write it in K omega representation, saying that Fk omega is omega minus omega k plus I gamma, and incidentally, let me write it like this. And then plus nonlinear term, which is f of f, and you assume that this f is Gaussian, that would give you standard, like in the quantum field theory, weak decoupling, namely that any moment of f's, which would come here when you compute this, you would decouple according to Gaussian or weak decoupling, and this is the first non-vanishing coordinate. Actually, we discussed that when you write the equation on dnk dt, it's a sum over 1 to 3 lambda, well, imaginary part of lambda a1, a2, a3, a4, right? So in principle, the first non-vanishing term appears when lambda is complex. It has an imaginary part, then you take here just a Gaussian product and. So that in principle, the lowest order in which it appears for a very special case, when your Hamiltonian already is with time reversible. But what we discussed that it's not a real kinetic equation, it is actually a Hamiltonian equation. It's called induced scattering in plasma. So let's forget it now and go to a standard kinetic equation which appears lambda is real. So this equation is just the first non-vanishing order of perturbation theory. Okay, so now what I want to do, what we start now today's lecture, is the properties of this equation. First of all, are there general properties? Apparently, all these equations conserve momentum. So if you just take nk and let's treat this as also np's, right? Just instead of rho, I'll be calling it np np1 np prime minus np1 np1 prime. So if you take k and k dk, it's a vector, it's conserved. If you take omega k and k dk, it's conserved. Moreover, this equation has an extra integral, and also they both have. So if you just take nk dk, it's also conserved. Okay. So because what we consider is a scattering, namely we have two particle scattering, or we have four wave scattering, two waves scattering to four waves, and total number of waves is conserved. Which means that at some point, a little bit later in this lecture, I would consider a different Hamiltonian, which I would call the 1, 2, 3, A1, A2, A3. Those are processes of decaying. One wave decays into two other, or one particle decay into two particles, and complex conjugated term. And for this Hamiltonian, we can also derive kinetic equation. It has one nonlinearity less, so here will be quadratic combination. I'll write it later, but it's important that in this case there will be no such consideration. And in this case, there are such considerations. Okay.
So this conservation, since you are kind of truncating your series.
Yeah, what we discussed in the first lecture, that generally you write Hamiltonian for I don't know what, for sound, for waves on a surface, for plasma waves, and it has quadratic term. It just describes linear propagation. Then it has cubic term. Then it has quartic term. So generally, you need to treat the first non-vanishing term. But what we discussed that you actually need to treat the first resonant term. So you take into account this term if you, and we last time assumed that if you have omega 1 plus omega 2, this is, and you have omega 1 plus 2, if such exists, you need to take into account this term. If there is no such wave vectors k1 and k2 that you can satisfy this relation, then you can exclude this term from Hamiltonian by a canonical transformation which is close to identity. And what we last in the first lecture assumed that we already excluded it. But today I'll actually consider a bit more general situation. I'll also take assume that cubic resonance exists. But for now, let's just talk about it.
So the conservation laws are exact regardless of which order you are in that.
Conservation law are exact for any n's. Your n's could be non-stationary, whatever. Just these delta functions, which are here, they impose this conservation law, and the symmetry between 1, 2, 3, 4, because it's scattering like this, it means that you conserve the number of particles. Okay. So now, because they are kinetic equation, apart from the conservation law, they have a very important property of H theorem. Namely, they are irreversible. There exists a quantity S, which is monotonic, which is non-decreasing in terms of this equation. What is this S? Last time we said that if you just take Boltzmann equation, when we still wrote it with rho, The moment we see rho, we always know rho is a probability distribution. We always know that entropy is just a Gibbs entropy, which is a sum of P rho P. And indeed, one can take this function, differentiate it, substitute Boltzmann equation, and just by the fact that x minus y logarithm xy is non-negative, that you show that the entropy time derivative is non-negative. What is here? What is entropy here? N log n? From time to time, I'll be asking you.
I mean, the probability
We should
distribution,
wake you up, but yeah.
I mean, the idea is, I guess what I don't understand is the probability distribution is if it's approximated as,
This is the moment. N is a moment, it's not a probability.
right, no,
distribution.
but underlying it, there's a probability distribution.
Underlying it is a probability distribution. It's a very good.
It's a,
Which probability distribution is behind this kinetic equation for waves? What I assume that my probability distribution is close to what?
factorized.
It's factorized. My distribution is factorized. Namely, the probability distribution. Well, let's use the same rho of a all set of AKs. I assume that it's completely characterized by those NKs. That's why I write an equation which is closed in terms of NKs. Which probability distribution is completely characterized by the second moment?
Calcium.
Gauss. So essentially, what is behind this Pile's kinetic equation is a statement that it's not only a product of a K, but each one is a K complex modulus over NK.
If that's true, how do you get the multi-prime correlation function?
Exactly, which means that it's not true. There is something over here, and it is precisely the third cumulant which gives me this kinetic equation. But when I'm interested in entropy, I assume, and this assumption is now questioned, that this small cumulants would give me small contribution into entropy. And it's true for equilibrium distribution. And I don't think it's true for turbulent distribution, but nobody actually were able to compute the contribution of these cumulants into the total entropy. Okay? But if you assume that your probability distribution is close to Gaussian, how the entropy of a Gaussian distribution is related to its variance? You remember? Well, you take this rho, you compute minus rho log rho, and you integrate over all possible values of A, and of course it's logarithm NK. Modulo pi, E, 1/2, and all this. Okay, so for every Gaussian distribution, entropy is proportional to the logarithm of its variance. Okay, and which means that if I'm interested in the entropy of a wave system, what I need to do is I need to consider S, which is the sum over K logarithm NK. Is there anything to bridge these two expressions? If I write this, again, I really, for a while, until maybe tomorrow, I'll start to work more on one side. But for now, I really want to work on both sides and on a bridge between them, so that you would see really the whole picture from. So, what bridges these two formula?
You mean the positivity part of it, or?
There must be some formula. Look, this is the kinetic equation, right? So it has a quantity for which ds dt is non-negative. So this kinetic equation has this, and it has a meaning of entropy of a Gaussian distribution. This equation is equation only distribution. So for any distribution, it has this entropy. Right? When you differentiate, there's a very different expression. They're both non-negative. When you differentiate this ds dt, you get something which is like combination of this n's squared. It's not similar to this, so kind of the technicalities, and I don't do this computation. You can look into book, you can do it yourself. What I now want to ask you is, what is the formula for entropy which goes in one limit to this and another limit to that.
NP plus 1 log of NP.
Yes, absolutely. That must be something which is related to this equation, which is simply entropy of a Bose gas. If you take a Bose gas, right? So what is the entropy of a Bose gas? It's a sum over K, nk plus 1 log nk plus 1 minus nk log nk. That's you remember where it came from? You say, okay, I have G states, I have n particles. How many ways to distribute this n particle over G states? So you get something like G plus n minus 1 factorial, and then here is the G minus 1 factorial, and here is n factorial. This is the total number of ways to distribute n particles over G states. G minus 1 is the number of walls between states. So you do Stirling, right? And then you actually express everything. This nk is actually n over G for a given k. It's like an average number of particles at a given state. So that's the formula of a Bose entropy. And apparently, when n is much larger than unity, it goes in one limit, and when n is much less than unity, it goes in another. Okay, so this you see that you can get both this and this, and of course you can also differentiate this and get non-negativity out of this quantum kinetic equation. Okay, so in this sense, when you really know what is Bose gas, you can do both, right? You can do kind of actually this equation is much more has a much wider application, a physical applicability than just a quantum limit of a Bose gas. It's just classical particle also satisfies this equation without any quantum mechanics, right? But still, I mean, it's nice to have this bridge. Okay, solutions. Now let's do solutions. So first of all,
There can be never a fermionic analog of the.
there is no, I mean, fermionic do not have a natural classical limit. That's a problem, right? So you want to have a classical wave, that's a Bose limit. That's the limit of quantum Bose gas.
Is it like the historical this is it why Rayleigh jeans actually were able to only use thermodynamics to define this relationship? Because Planck, the Rayleigh jeans was already there, and Klapko gave the other tail, but the Rayleigh jeans never use any quantum thing, just
Exactly. So now let's do it. Let's bridge Rayleigh jeans with Boltzmann via. Okay. So here will be Rayleigh jeans, which will be nk t over omega k, and here will be Boltzmann, and p is exponent minus epsilon t divided by t h omega k.
But was it what they did?
So what bridges these two limits?
Planck.
No, of course. So if you take this entropy which I just erased, and you require that your entropy, well, let's do it. Okay? So what is a standard way to get a probability distribution? If you know something, you say that it is this famous mantra of the truth, the whole truth, and nothing but the truth. Okay, that's how you find probabilities, how you find any reasonable hypothesis. So you say that, imagine what you have your fixed energy, which is the sum of a k of omega k and k. Well, you can add h bar for the heck of it. And you say, okay, but I also know momentum, right? There's an integral of motion, right? So there is something of k, it's a vector, right? K and k. Or you could have also a number of particles. You could have some other things. Or I know something r, which is something which is, let me call it yeah, R. Mean, which is R of K's and whatever n K is decreased. Something else, you just know it, right? So you say, I want this fixed, I want this fixed, I want this fixed, and I don't want to add anything fixed. Now you ask what would be your probability distribution. You say that you need to, because this part of the sentence, nothing but the truth, means that you need to maximize your missing information. So you sure you do not assume anything except these things, right? This is a general framework. It's common sense. It's nothing else but common sense. You say that you want, under a given condition, the distribution which is open to maximal possible possibilities of including anything else, which maximizes entropy. So if you do it for a quantum gas, which you say that this is nk plus 1 log nk plus 1 minus nk log nk, this is your entropy. But now you add here this lambdas I and the sum over I, all your Ri's. Let's say this would be your R1, this would be your R0, right? Just all functionals. What is important that they are linears in n's. Okay. So now you say that this is a functional which you wanna vary with respect to nk. Then require external. Okay, this is a very, very general statement. So what you get out of it, you get nk plus 1 over nk when you vary it. When you vary this, it just will be normalization. When you vary this, you get log. When you vary over this, you get log. When you vary over this, you get the sum of lambda I R of I. All your conditions that you impose. They aren't necessary integral of motion, right? These are integrals of motion. This guy is just could be something. You just happen to measure something, and you want your distribution to have this mean work. So what you get out, of course, is Planck, a kind of generalized Planck. Over some t minus. Okay. For a particular case where all these things that you know are integrals of motion, that what stands here are again integrals of motion. And the way that Planck wrote it, there was just no overall motion of your system. There was just sum over k, h omega k over t. Now, of course, this, when you assume that nk is much less than unity, so you are in this limit, it means that this exponent is very, very large, and you get Boltzmann, right? Now, when you assume that you're in the limit where these terms are very, very large, it means that this is very, very small, it's close to unity, and you approximately get okay. Now, if you want to include your momentum, what you would get just minus k times some v, which is the external parameter, which tells you essentially that you are looking at your distribution from a reference frame moving with the velocity v. And the same you can get here, which means you had a drift. What it is, it's like a Doppler shift, right? So you are moving, but it also tells you that your solution has a Galilean invariance. So if those are your momenta, your all momenta are shifted. So what it would be if you would be working not at quasi-particles, but your energy here will be some energy, and this will be minus kV. So you would get something, it's a distribution which would be, it's a distribution probability of having velocity v, which is a momentum divided by mass. So you would get just Maxwell in a shifted, reference frame. This is a kind of something which is sheer triviality, but the moment we pass through turbulence, we'll lose this symmetry, and it's really interesting and important how we actually lose Galilean invariance. But this is something which just comes from a sheer fact that in the equilibrium, when we look for the maximum of entropy, all our integrals of motion come as a sum. And of course, this is the result of our underlying assumption that we are working with a distribution which is when you divide your system into subsystems, for example, for waves with different keys, they have independent distribution, so the distribution is a product. And so if your distribution is an exponent, it's an exponent of a sum of your additive integrals of motion. So the additivity of your integrals of motion is translated into the fact that when you take exponent of their sum, it would be a product of independent distributions for subsystems. Each subsystem has its own integral of motion and they sum. Okay, so that's equilibrium solution. It apparently realizes the extremum of entropy, and it's actually even more general because in this particular case there is a third integral of motion which I erased. The number of particles, the total. And of course, what corresponds here is just you can have a constant, like kind of some chemical potential, because when you conserve the number of particles, then you generally have a non-zero chemical potential. For the cubic case, of course, when you do not conserve, the chemical potential is zero. Okay, questions?
Yeah, so this exactly what my question was going to. So even if I have zero chemical potential and I don't have particles, number of particles to be conserved, when I take this limit and we go back to Boltzmann, it seems that I recover number of particle conservation.
It's only when you consider this Hamiltonian with quartic interaction. When you do it with cubic, there is no transition to Boltzmann. Boltzmann is this process, right? You cannot get out of decays and confluences of particle Boltzmann limit. That's why I did it, because normally when I teach it first cubic and then quartic. But because your people spoiled by quantum mechanics, and so I wanted to have H bar from the beginning, right? And if you really want H bar at the beginning, then you work with scattering, not with decay. Then this one nature. Okay, good. This was easy part, equilibrium solution.
Sorry, one more question. But can I tweak this? Because when you wrote this collision intro, you assumed that the number of particles will be conserved. Can I actually modify it in a way that?
Yes. I want to do that a little bit later, but let's do it now. So if you have this cubic Hamiltonian, so what kind of again, you do the same equation, but now what you would have here, you would have a sum of a 1, 2, lambda k1, 2, and it will be a1, ak, a1, a2, and it will be also ak, a1, and twice ak, a1 complex conjugated. So if you take this Hamiltonian and you vary it with respect to ak complex conjugated, you would have these two terms, right? So now, if you multiply it by k complex conjugated, and this will be equation on d and k dt, what you find out that it will be, again, imaginary part, ak, a1, a2, something like this. So you would have a short moment in the right-hand side. Then again, one way to do it, you can write equation on the third moment. It would be expressed in terms of the fourth moment. The fourth moment you decouple by Gaussian. As a result, you substitute it here and you obtain the following equation. well, I call it V, right? So it's V K1, 2 squared N1 N2 minus NK N1 minus NK N2. This is a process in which your K decay into two particles. But there is an inverse process which corresponds to the fact that you can have your K with some one come into two. Okay, so here you would have V2 1K squared, and it will be N1 NK minus N2 NK minus N2 N1. And with all bells and whistles, there will be K2 minus K1 minus K here. There will be delta function of K minus K1 minus K2, and there will be delta function of omega K minus omega 1 minus omega 2, and the same delta function here. And because here, one, you can choose 1 and 2, there is extra factor 2. So that's a kinetic equation which I guess Piles wrote first this equation. Because when you start looking at phonons, and that's what people were started to apply, it's a quasi-particle space for phonons, then naturally you have this anharmonism which give you this. Do you remember, Vladimir, what was this what actually the first kinetic equation that Piles wrote was this equation with quadratic ends and not with cubic like for scattering. Okay.
I only cite this paper because you cited I've never opened it.
It's translated because I remember when the first time I looked at it was in German. That was his dissertation. And so, but I had rumors. The guy who with Landau actually used first this equation to compute the relaxation rate of sound in solids in 1935. So the rumor was at that time alive, and he was in Novosibirsk, and so he kind of helped me a little bit with it. Anyway, it's translated now, and you have Piles, all Piles work. Okay, so now we have four equations. I hope that you really can keep. So we have a triad of four scatterings, which is four-wave scattering with cubic term, quantum with n+1s, and Boltzmann. And on top of it, we also have a kinetic equation for triple processes, for decays, and it has this form. And essentially, what we'll be doing is mostly, and of course, this equation has only this solution. It does not conserve number of particles, but it still has, as a general form, this solution. You can plug it here, and you can just see that by virtue of this, that when you have here sum of omegas and sum of one of a simple ways to see it is just write this as following. You write it as nk n1 n2 1 over nk minus 1 over n1 n2 minus 1 over n1. So if your 1 over n is a sum of integrals of motion, then this turns into 0 by virtue of this, right? You see it? And the same for quartic equation. If you take four n's out, you have 1 over n plus 1 over n minus 1 over n2 minus 1 over n3. Right? So if you have Rayleigh-Jeans essentially as the limit of Planck distribution, it's 1 over sum of integrals of motion. Right? So that's how you get this. Okay, good. Questions? Yes.
The one way you said you can derive the kinetic equation is by adding forcing dissipation. So can you get the Boltzmann equation that way?
No.
Why not?
I don't know. It could be possible. I'm not saying that it's impossible. I said that I don't know how to do it this way.
But you got between the two. You said just do the quantum wave case. So we do the quantum wave case. We introduce forcing, and we just always assume n is much less than 1. So you got the Boltzmann.
As a technical, yeah. As a technical, this means that.
But I mean, you got the Boltzmann in the assumption that.
In a sense,
interactions are-
the question is how to do it in quantum, because the moment that you do it in quantum, then you kind of do it in both ways. I think that you can do it in quantum, namely that you really assume that you have forcing It's not non-trivial because essentially what you compute when you derive quantum kinetic equation is you compute matrix element between transition between n and n plus 1. It's a quantum transition. There is no classical analog. Okay, so you would probably need to do it not by forcing, but by saying that you add something which causes kind of this random transitions, and then you would need to ask what would be the rates of these transitions.
But I'm not sure, sorry, I want to make two comments. So I think the forcing term, as we discussed last time, on the harmonic oscillator, the force is A plus A dagger, so it does make transitions from different. You know,
Yeah.
in the quantum line, so the force, the actual force does do what.
You mean that you just add to the Hamiltonian a term
source
which is
term.
linear,
In
in
field
creation and
operators, yeah,
annihilation,
right.
and you assume, but there would be no dissipation.
Right, I think dissipation is the thing that I'm less clear about. The thing that I learned last time, which I've seen in previous notes, but it hadn't registered, is that certainly the sort of Zaharoff trick of taking a ratio of forcing and dissipation to n, if you were thinking in the quantum, you know, n is not a number, n is an operator, right? So it's kind of like a very strange thing to have a operator value. Right, and if that's what you're asking for, then that's in the quantum case, I don't know.
I think you can do a Caldera-Leggett like trick, right? You enlarge your system to quantize it. I mean,
Yeah, okay, anyway, I'm not sure. I don't have the answer, it's just like a
Again,
question.
generally, for example, the trick that we do for non-equilibrium, let's say, right? So that you kind of attach it to other big system, which is the thermostat, right? Because in a sense, you must say that if I would be deriving it, I would say, okay, my Fk comes from thermostat and my gamma k comes from thermostat. So what you can do, you can again treat your quantum system as a subsystem of some big system. This is one of the way, which is probably would be, and then you trace out everything out there, and then you assuming something, and then you probably obtain. Would be interesting if somebody does it, and
I kind of,
won't be.
I've kind of worked on that a little, or tried it a little bit. The Schwinger-Keldysh method lets you do this. Like you can integrate out some coupled to some harmonic oscillators. You get something like a forcing and dissipation.
Yeah.
And if you do the standard way to get a kinetic equation from there, it looks very similar to what we're doing with this path integral, the stochastic path integral, classical in the way of kind of.
Yeah, when you write already path integral, this already there in a sense. You can get out of it. But the question is, can you do it on an elementary Hamiltonian level of a
And
dynamic?
I think the Schwinger.
So I think that
you can add like a couple of Markov oscillators to your degree of freedom, enlarge the system, and then just
yeah, that's what I think. That you
solve for the bath and put it back into the system, and then you get the Langevin equation from there.
one of the way, for example, like what Zamolodchikov, how he derived it, almost exactly solves the problem of a current, you know, in this washing, that you kind of attach it to a Bose system of quasi-particles which interact with it. And then you find out that the big quantum problem is integrable, then you trace out these other things, which is technically, I've seen it a couple of times, and it's so complicated, it's so technically involved that I wouldn't do it. Okay, I want to move to turbulence, so let's just leave equilibrium now. Very briefly, I remind you that, of course, Boltzmann equation also used for non-equilibrium solutions. And usually, at this point, you start to realize that what you started from, of course, was also integral over dq prime, dq1, dq1 prime. So everything is also in space, right? And if you look for solutions which are uniform in space, then this integration normally give you a normalization factor, but generally you have space dependencies, and more or less the straightforward generalization of Boltzmann equation for out of equilibrium situation, or when you take, for example, this distribution of probability of velocities, which I just erased, so it was just m V minus V squared over 2t. And you say that this two macroscopic parameters of this distribution, for example, so you have both of them depending on the coordinates, right? And this is the simplest way to generalize. Of course, you cannot now do it for arbitrary dependencies of t and v, right? So you really assume that locally your dt dx divided by t is some kind of a typical inverse length, and you assume that this length must be, I mean, this is inverse length must be much less than a mean free path, which you derive in terms of the kind of this scattering probability. So usually the mean free path is a scale in which your particles substantially change their probability distribution, and this mean free path naturally comes out when you now take this distribution and plug it here. You immediately find out, well, then you need also to add here to the left hand side that what stands here is V dx dx of rho, right? So now you, apart from d rho dt, you also will have on the left hand side this term. So when you differentiate this distribution, you find out that you have a left. Then you need to assume here that your distribution is not only this, is something like 1 plus chi, and this is the sum correction to your distribution. It's a non-equilibrium correction to the equilibrium distribution. When this is a constant, this is the 0, and you plug it here, you linearize this part. So it will be chi plus chi prime minus chi 1 minus chi 1 prime. Again, those are momenta of the distribution. This is a standard thing which you probably learn how you do. It's a kinetic, standard classical kinetic theory. So you get the equation in which in the left side will be the derivative of your t and derivative of your v, and in the right hand side will be your correction. So you find out that your line must be proportional to your gradient of t, and v is a derivative which is what we found out is a tensor of and this would be the t dx alpha. So you would have some kind of a vector correction to it, and you would have some you find out that what stands here is v alpha v beta, and then you plug it, and depending on the form of this scattering, and it's usually ugly computation if you really want to be specific, but then eventually you call some integrals, just 1 over L, which is a mean free path. And in this way, what you get an expression for thermal conductivity, namely this correction chi would give you the flux of heat, because the equilibrium solution has no flux, it has a detailed balance. Now this correction deviates you from thermal equilibrium, namely that it breaks detailed balance. You would have a direction of a heat flow in some, and you have a flux of momentum over here, and the coefficient between the gradient of T and the flux is called thermal conductivity, or in this case, it's called viscosity. So that's how you compute kinetic coefficient. That's what one may say classical kinetic theory. Okay. In principle, you can do all the same in this case, right? So this is your Rayleigh-Jeans distribution. You can do this function of coordinate, you can do this function of coordinate, you can do this function of coordinate. This way, you obtain thermal conductivity, let's say, due to phonons. Okay, so you impose a gradient of temperature, your quasi-particles of wave, let's say phonons or anything else, and they will bring a flux of heat. Or the same way you can get a flux of momentum, or you can get a flux, a diffusion of particles, if you have a gradient of the chemical potential. Just whole standard stuff, and there are textbooks on both things, right? So this is more or less like 100 years ago, or this is more or less like 70, 80 years ago, which is pretty old stuff. This was a little bit later, but again, Piles derived this equation precisely for such calculations. That was his goal. And then Landau and Romer computed it for sound in dielectric, and then there were people who were doing it for spin waves. Whatever, all which comes out of it is kinetic coefficient. Namely, proportionality between the gradient of your macroscopic parameter and the flux of a respective quantity. Then you may ask, are these distributions, which I don't want to derive, right? I mean, I can do it, but it's kind of classical kinetic theory. I want to move far away from equilibrium, but still I want to say a few words. This correction, you can compute them, right? Or you can compute it here. And then you ask, do they satisfy any extremal principle? Because equilibrium satisfies extremum of entropy under a fixed integrals of motion. Okay? And then you realize that all these corrections, they do satisfy a principle which look a little bit artificial, but its formulation is that it's a minimum of entropy production rate, or the rate of dissipation, because you are in a close to equilibrium state. You linearize with respect to this correction. You are near equilibrium. Your deviations are infinitesimal. So you have the Ansager relation on symmetry of your kinetic coefficients. Remember that if you have a force x capital and the coordinate x small, and then your entropy production is usually products of x small times x large, etc. And you look at it, essentially what you're doing a quadratic deviation near equilibrium. Equilibrium is an absolute minimum. So you can kind of imagine that you have kind of a landscape in which you a little bit deviated in some direction, and then it comes down. It comes down by which trajectory? By the shortest, right? Because you are still in a parabolic profile. If you would be far away from equilibrium, there's no such principle. So I always thought it's I mean, back at Leonard 50 years ago, Prigozhin advocated universality of this principle, but when you look at it, you just realize that this statement or this extremum is just an Ansager symmetry. It's just a statement that you have a nice parabolic profile near equilibrium, right? I don't know. There is maybe more to it. There are some, in a very trivial situation, which is not part of this course, but there is something which is called stochastic thermodynamics, where you treat system with like 1 degree of freedom or like 2 degrees of freedom. And there you can get, and it's in a contact with the thermostat, but in a very non-equilibrium state. You can kind of run current of probability. And then sometime it's always, you can find out that even for very far from equilibrium state, in these simple cases where you're in a contact with the thermostat actually provides you with this return force. You also have this extremum principle. Its degree of universality is unknown to me. I was never able to derive it in anything which would be kind of turbulent-like situation. But it doesn't mean that it's impossible. Okay? That's all I wanted to say about near equilibrium. Okay? If there are any questions about classical kinetics, ask it now, because now we'll move to.
Sorry, when you said parabolic potential profile, is this parabolic profile of entropy?
Yes, it's parabolic profile of entropy. So in a sense, well, I always look at minus entropy because we like to see.
No, sorry, that was my confusion.
Yeah, it's not energy, it's entropy, and you go to maximum. But you know that people who invented entropy, they actually had all this analogy with mechanics and variational principle in mechanics. So they were really looking for something which is an extremum, and thought that in this mechanical sense. So, but in this case, yeah, you go towards maximum. Yeah.
Can you explain again how the fact that entropy is parabolic around its optimal value corresponds to minimizing the entropy production rate?
You see, it's technically it's like this, that you let's say look at this as an operator, when you linearize it, it's a linear operator acting on chi. Okay, so you would say that you have on the right hand side like ddt. Here this gives you this gradient, and this gives you some linear operator. The first question that you may ask about operator is whether it's Hermitian or not. Namely, what are their eigenvalues, right? So as eigenvalues are negative, namely, every deviation from equilibrium, if you leave it alone, namely, you would not impose a gradient, would go down.
What is the boundary condition that you're applying here?
The boundary condition, so it's a very good question. Again, I'm not teaching you classical kinetics. You need to require that all the integrals of motion are the same with this deviation.
And that quantity.
So the integrals of chi with k, omega, and just chi I zeros. Okay, those are something which fixes, because otherwise you would have even you can always shift this by an arbitrary thing, right? By an arbitrary constant. Okay, but well, generally it just tells you that what you find if you impose a gradient or the same, because in a sense you are still within the linear regime around equilibrium. So you have a fluctuation dissipation theorem, which tells you that if you are going to ask what are the correlation between fluctuation, you can just wait until this fluctuation appears and see how it dissipates. That would give you the same correlation between, let's say, some quantity, some coordinate at different moment of time, right? And so this linear correction are essentially within this regime. And the steady state in which you can impose it, it's again such a state in which you have a maximum of entropy production, assuming all this that you impose all the normalization of your perturbation. But again, I don't.
Sorry, I'm confused. So, right, so if it's parabolic and it's a multi-dimensional space, we are going to linearize everything, and there's going to be some amplitudes and rates of relaxation. And the latest, so there's going to be a whole spectrum of rates,
right? But
and that's not really up to me.
Right. Now you're exploring one direction, namely that you have a low temperature. You can impose electric fields. There will be another direction, right? You can impose a chemical potential. So this is something which is kind of this. But on the other hand, you can look at it this way: that if you look at the dissipation, it would be a gradient T squared. If you look at extremum of it, it means that your equation must satisfy the solution locally, that Laplace T is equal to 0, which tells you that your profile on T must be linear. This is one of the applications. You can get it by name Kirchhoff if you treat conductance, for example, right? This is essentially that some quadratic, because you are working in a linear approximation, your dissipation is quadratic. And requiring this quadratic is, in some sense, means that you need to assume that this is constant, and if this is constant, that tells you what is your distribution. Let's move to turbulence. So now what I wanna do, I wanna erase everything but this equation. Okay. So I'll start from really simplest case, and then I move to the following case. So let's treat something which we just get recently, namely this kinetic equation for three-wave processes. This is the simplest form, and it has much less solutions. So this equation has only two integrals of motion, namely energy and momentum. And I want to assume that everything is isotropic, namely the momentum and variable. Okay. So what I want to say is that if this equation is the sum over k, omega k, dnt dt is equal to 0, right? Then I can take this equation, multiply it by omega k, and call it dak dt. It's just a time derivative of a spectral density of and because the sum of it is zero, then I may say that it is in some sense dak dt, it's some kind of a divergence minus of some flux. Right? Because if something is conserved, and you can kind of formally say that there must be a continuity equation for it. So if you now integrate over t, this will give you zero, because you assume that at infinities, this is important already assumption, that you assume that in infinities in k space, namely at 0k or at a very large k, there is no influx or outflux of our particles. And then you say that in principle, we obtain a solution for our equation. You know, in this case, there is only one parameter solution, which is relations with omega. There is kV, but everything is isotropic for now. It corresponds to pk equal to 0. That you can just see, because if you plug this in 1 over omega, here would be 1 over omega, it would, every term just turns into 0 identical. Right? So this is a equilibrium solution. Equilibrium solution has no fluxes. Right? Now we say, what is there if there is a solution which corresponds to a flux which is a constant?
So you're writing the right-hand side as some divergence of P.
Yes. So my P is essentially some integral of all this. Again, because we assume that everything is isotropic, let's do it in a spherical normalization. Namely, that I would introduce k d minus 1 omega k and k at some ek. Is a energy kind of in a spherical normalization, it's just one 2 pi with the right power. So then I would have my equation in the following form. Well, just a derivative with respect to wave number, and I will call it pk, but now this is pk is the flux through the sphere. So I have a sphere at a given k, and then pk is a radial flux through the sphere. Okay, and what I look for the solution where it is constant. Okay, now the question is what physically I have in mind. I have in mind that somehow on the boundaries, my conservation is broken. Let's say that at a very small k, there is some source of my particles, which just adds, or my waves, which adds them. And at some large k, there is some dissipation mechanism which kind of removes. Or it could be other way around. But in this case, it will be like this. So what I now want to see, it's a very complicated integral equation now. This equation is now very complicated because what stands here is the following thing. It's an integral from 0 to k d minus 1 dk, omega k, and then all this stuff. The integral over dk1, dk2, vk1 to where n ends, all the kinetic equation, right? So what I need to solve, this integral. There is delta function of omegas and delta function of phase. Okay. So what now I really need to solve this integral equation? It's very complicated. But we now may consider a subclass of systems which are scale invariant. Maybe I have extra symmetry and I can now exploit it. So what I will assume that my omega k in a scale invariant situation, it just must be a power law. And I assume that my v so I assume that, of course, this is some function of its ratios of angles between k's, etc. Interaction of waves depend on which angles they are, but it scales, namely that it's just proportional to k in some power n. And so now what I want to try to do, I say, okay, it's a complicated integral, but let's just estimate how it scales with k, right? So what you would get k to the d from here, alpha from here. You would have here 1, 2, but one extra. So you would get another d from here, from integration over case minus 1 delta function in case. You would get omega here with a minus alpha, right? You would get v give me plus 2m, because it's a square of my matrix element. So now I say, if my n k behaves as k in the power minus gamma, then it would give me here minus 2 gamma. That would be the total power. This is just power counting, simple power counting, right? Boom, 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 boom. So alpha disappears. It's an interesting and important lesson here that I'm interested in the constant flux of energy. Energy is omega k nk, and the scaling of this flux is independent on whatever is the scaling of frequency, because it comes in two places, here and here, right? Because this is something which enforces conservation of energy in every elementary act. This is energy itself. So what I find out is that gamma is equal to m plus d. It's Zakharov to get this formula for a very particular case. It tells me that if some conditions are satisfied, then nk in the power minus m minus d is a stationary solution of kinetic equation. It took 50 years between derivation of the equation and finding its stationary far from equilibrium solution, right? What are the conditions for this to be a solution? This is a power counting, right? Then one asks when power counting actually works. This is a nice way to do theoretical physics. You just count numbers and that's it. You get an answer. And so what are the conditions? What we need to now check? Well, we may take this and plug it here. It's ugly. Even for very simple V. So let me tell you what Zakharov did. This is also interesting to see how other people do their PhDs. So he was doing his PhD, and he considered a very specific case, phonons, which has a very simple matrix element. I mean, this V is essentially k, k1, k2. Well, there are some cosines, there are some cosine. They're essentially scalar products between them in the power, and it's a square root. So the square root of it was just a product. Means that if you really do your job and integrate over all angles, what would eventually come out, there would be some powers, and there will be integrals with this form, but complicated combinations of them with exponents. Now, then what he did, he checked that in this integral, if you look at it as a function of gamma, he found out that it diverges in infrared when gamma hits 5. So if it's too steep, then it's at 0, the integral diverges. And he checked that this divergence was actually positive. So it was turning into 0. So in a sense, what he was doing, he was calculating this as a function of gamma, or rather this integral, which is the integral, let's call it I. So he was calculating I of gamma. And he found out that it was, because it's easy to see where it started to converge. It's non-trivial because there are some cancellations over here. When let's say 1 and 2 go to infinity, they are very close to each other because 1 minus 2 is k, and when 1 and 2 are very, very large, they're very close. So this is one cancellation, but one power. You don't need to do this all carefully. And you can look in the book. I'm not going to go into it. And then he checks that when it's 4, it diverges in the ultraviolet. It's now not steep enough. It decays too slow. So, and this is negative. Okay. And this is trivial computation. In a sense, checking divergence of or convergence of integral is relatively simple. Because what you really need to do, you need to take this asymptotics. This is actually symmetric product, so it's kind of just straightforward. And then you just again see modulo these cancellations out of this combination. And then it's okay. Then somewhere it changes sign, right? So my collision integral as a function of gamma, where gamma is a scaling of nk, somewhere turns into 0. And so he tried 4.5. Now, for specific number of gamma, it's non-integer, so you get some beta functions. You get some 18 beta functions, and they all cancel out. Okay? And so this is such a function. So this is a really very non-straightforward way. No argument about power counting he did not know at the time. Was just doing straightforward computation. Then in my PhD, I proved that it's always in the middle. In a sense, for this, it's kind of a formal exercise to see that this divergence and this divergence, they are exactly such that the stationary solution is in the middle. In a sense that it tells you that this cascade solution, which takes energy from small k and conveys to the large, somehow have interaction with large k and small k balanced. But again, it's something. But now, and then a couple of years later, he realized that you can actually do simple power counting to get it. It's really amazing that you first do complicated computation and then find a trivial way to get the answer, right? Which is power counting based on the conservation law. Okay. So you already from here you see that what are the conditions that this is a solution. When you can estimate the scaling of an integral by simple power counting.
When it converges.
When the integral converges. There are triple integration over here. This is integration from 0 to infinity over k1 and k2, and integration from 0 to k over k. We must be sure that this integration over k1 and k2 from 0 to infinity would not include UV cutoff or IR cutoff, because it would change power of k's, right? If we would have somewhere. So what you need to check, you need to check convergence, which physically means locality. Locality in this sense is a locality in k space. If this integral converges, if this integral over here, you plug here k to the minus gamma in the integral converges, it means that the main interaction for a given k gives waves which are comparable to k. What else we need to assume to have it a solution? Well, we need to assume the equation itself is valid, right? I don't want to be. The kinetic equation is valid, assuming that this part, this system of a Hamiltonian is small relatively to this. And we discussed it in the previous case so we need to say that there is some kind of a V having or in other terms, we may say that if we look at the typical time of interaction, 1 over tau from this kinetic equation, it's V squared, it's n, because it's quadratic in n, and I canceled one n, and it's k to the power d, right? because there are two integration over wave numbers here and one delta function. And there is one over omega. That's my typical nonlinear time of interaction. And I must assume that if I take it dimensionless, that my typical nonlinear time interaction is much, much larger than the period of the wave with which I work. So I need to assume that this is something which is much less than unity. This is not a validity of a solution. This is the validity of the equation. Okay. So technically, at that what immediately avalanche of work started, like, I don't know, 50 years ago, and there was people. The first thing, you write your equation, you look at your physical situation, you find out the interval of parameters in which your interaction is weak, then you call it weak wave turbulence, and this is the term which appears at the time. And then you write kinetic equation, then you plug your solution, which you get from dimensional reasoning, and you compute convergence. And then I remember when I was doing my PhD, I was mostly computing convergence, integrating. There's sometimes very non-trivial consolation. What is important lesson, particularly for people from a condensed matter or quantum science, is that in this case, nk is k minus this is the scaling. So if you plug, so let's call it epsilon k. Well, epsilon is, I don't know, this epsilon. So it's a, as you would see, my dimensionless coupling constant. It's my parameter of nonlinearity. It's dimensionless, and it's a function of k. Namely, as you go in k, it could increase or it could decrease. So if you now plug here your solution, then you would get this as k to the power 2m. This you would get minus m minus d, right? This you would get plus d, and this you would get minus 2 alpha, right? And what you find out, first of all, which is a very counterintuitive for condensed matter people, the space dimensionality cancels out. That your turbulence does not actually care in how many dimensional space it lives. It's isotropic turbulence, right? Your flux in it's a radial flux in Fourier space, but dimensionality of Fourier space is irrelevant. Because when you increase dimensionality, you also get your solution steeper and steeper, right? So it means that all hopes that you can have something like limit of large d, which would simplify things, does not work here. Dimensionality is irrelevant. In this case, your parameter of nonlinearity essentially depends on the relation between how your interaction grows with k and how your frequency grows with k. That's what actually tells you whether you're nonlinear or linear. Okay. Good.
Can I ask a quick?
Yes.
question? Two somewhat related, but not directly. So usually, so there's an equation that has this solution. So there are two kinds of questions, right? One question you could say that, well, is this one equation for one type of behavior, and whatever choices you made to derive this equation completely rule out other types of solution, like equilibrium solution?
No, this equation has equilibrium solution.
Right.
This one.
So in that sense, is turbulence a spontaneous phenomenon? Like, what's causing turbulence?
What causing turbulence is a boundary condition
Right.
in Fourier space.
Right.
So if you have boundary condition in Fourier space which are linear, which are zero, then your only stationary solution is equilibrium.
Right.
Equilibrium is a solution of this equation, right? It does not correspond to this power counting, but it just has flux identically zero everywhere.
So can I think of this flux as a knob that I control?
Yeah, in a sense, you can say that what you're actually solving. You're solving this equation. you impose a boundary condition at k equal to 0, because the integral now of your is not a 0, it's a constant.
Yeah.
So it's a delta function. Okay?
Mhm.
So this is really the
And
equation.
so there's a
of this.
solution for arbitrarily weak.
And now it's a condition on this p. This constant is larger because what stands for here, your n is p 1/2
Mhm.
this, okay? So this constant, which is the power of your pumping, it what determines. So it's like what we want.
No, but it shows up for arbitrary, so I cannot have laminar solution with finite.
What do you mean
flux.
laminar solution?
As in
Laminar
solution-
is a type of a flow.
Right, no,
No,
yeah,
no.
so I guess my idea would be somehow that equilibrium is a stable fixed point, I can perturb around equilibrium. And so what I'm trying to understand is that this parameter controls the type of the solution. The moment you have arbitrarily small amount of that parameter, you're already turbulent. Yes.
Okay, now I actually wanted to have it on the next lecture, but let's
Okay,
not.
that's fine. I can
Let's
do it.
not
I'll be here.
talk about it. No, this is, I think that you're right, this is.
Okay, the other,
logically-
so can I ask you, since I might have to run, the other, a separate question was. Absence of dimension dependence, is this a feature of this sort of equation? And if I compute high corrections in interactions, dimensionality will come back, or is this not known?
Well, we didn't compute much, but at least as far as we see, dimensionality does not
I see.
appear there. So it's at every point. But now, yeah,
So this equation will never be satisfied for all case, right? And we're using.
well, it could be 0. I mean, this power could
Ah.
be 0.
Okay,
But generally, no, it's either there or there. What I really want you to appreciate is the fact that this window of locality exists. It doesn't, it's not always exist, but the fact that what I've shown that for acoustic waves, it was between 4 and 5, it's something about a very special form. Boltzmann, by the way, has also the same property. When you look at this kinetic equation and you look at the convergences or divergences, either in infrared or in ultraviolet, you will see that these differences make for cancellations, right? Because generally you have some integral. Now you have this thing, which means that everything is a power function. You plug power function in the integral, it diverges either there or here. How it could be that it, for some interval of gammas, it converges on both ends. And this is something which is a very beautiful property of kinetic equation, which is generally not shared by the next terms of expansion. And I don't know, there is some lesson here, but I did not know how to formulate it. And technically, when you look at kinetic equation here or at Boltzmann kinetic equation, there are always these differences which provide for extra cancellations. Moreover, there is some cancellation between this term and this term, because when one of them goes into 0, this is kind of always like, I mean, this is always almost like this, right? So there is a extra degree of cancellations, 1 degree of cancellation at infinity and 2 degrees of cancellation at 0, which provide for this window of locality. And then your solution can exist. But there are situations in which there is no window of locality.
It's not the same as detailed balance.
Absolutely not. This is a far from equilibrium solution. There is no detailed balance. In a sense, this parameter is your measure of how nonlinear you are. But the something which, if you look at K space, look at NK. So you have your pumping scale, right? And you have your dissipation scale. That's infrared and ultraviolet cutoff. The ratio of these scales is essentially the measure of how far from equilibrium you are. It is also the measure how strongly you broke the detailed balance. Because detailed balance means that you at every key you force and dissipate. Now you force here and you dissipate here. In usual hydrodynamics, it's called Reynolds number. A Reynolds number is exactly your degree of breaking detailed balance. So you pump at a large scale and you dissipate at a small scale. When you look in between, somewhere here, you need to read and know how much you broke detailed balance, because you carry this flux from here to here, right? And now for Vadim's question, before we end, because he asked this question, now let's briefly describe the relation between this solution and that solution. Because generally, I can say my general solution is a function of K, P, and T. Right? Because I can have, I say, okay, look, my quasi-particles, my waves exist in a medium with a finite temperature. It means that somewhere, for example, when there is a thermal reservoir and I have a temperature. On the other hand, I also on top of it imposed a solution which carries a flux. So how it would look like? Well, you can say that, look, dimensionally, you can write it like this, like T over omega K, and some dimensionless function of dimensionless combination. What is the dimensionless combination over here? You see that this is this solution, and turbulent solution you can write as P1 half and K minus M minus B. There are some constants which depends on your medium, but this is essentially how it looks like. Which means that the ratio of this to this is your dimensionless parameter. So you find out that this is here a P1 half K minus M minus D divided by T and plus alpha. Right? So now when I'm answering your question, it is this parameter which determines whether your turbulence is a small correction to equilibrium, or and it tells you that it's a function of K. So it's something which people really observe in many situations. Then you have MK as a function of K, and you have some kind of a turbulent solution, let's say omega K and K, and it eventually goes into the big equipartition. Greg is particularly fond of saying that at large K, it's always thermal noise, right? So, and there is some region in which you can consider it as a small correction to thermal equilibrium. It still carries the same flux, right? But it's
Even like out there where it's finite.
It's what we call hybrid solution. Okay. Now, what is a really interesting question is, and that's probably I already speaking for hour and a half. I still alive.
Can I ask a question?
yeah.
That's the solution of the kinetic equation for which F?
This is means that generally one can nobody ever found this function
Right.
except its constant plus small correction. Namely, you can take your Rayleigh solution and find solution of a linearized equation which carries constant flux. That would be an expansion with respect to small parameter of this. Okay. Or you can take Zakharov solution and make a small correct and linearized. When you linearize with respect to Rayleigh, your operator is Hermitian. By the way, when you linearize with respect to Zakharov solution, your operator is non-Hermitian. Nobody guaranteed you that the turbulent solution is stable. It's generally non-Hermitian. It's an ugly stability problem. Still, it's kind of doable. You can find equilibrium correction, which as a solution of linearized equation, right? And this is so you can find this function in expanding in the small parameter or inverting and expanding in the other small parameter. But the general form is unknown. It's called hybrid solution. Sometimes it's called warm turbulence. Warm cascade.
Is there something that guarantees that you'll find the stationary solution?
No.
So why do you expect a function of this?
Good question. In a sense, well, first of all, when you look at equilibrium, everything diverges. This just I don't know any physical situation for which integral converges. One over omega is too slow, right? It's just usually. But we may say that generally for some alpha and m and asymptotics of it, we can have it, and then we can think about analytic continuation, etc. But this is a very, very loose argument. This function exists in some cases, but not in general in all cases.
Just, can you repeat? So if I do some perturbation, linear perturbation on top of Rayleigh genes, is the Rayleigh genes, stable? Really, not the Rayleigh genes, Sahara, solution, is it stable?
Not always.
But sometimes,
Wait, what I'm saying is the following. If you consider the situation where your n is n k stationary plus delta n t. Now you can take this t over omega, linearize your equation. The operator that you have is Hermitian. Namely, if you don't have any source which generates your perturbation, any perturbation dies, guaranteed. Now, you take the same, you take NK0 Zakharov solution. Your operator is not Hermitian, which means that you can have now in principle instabilities. Instabilities, let me tell you, the fluid mechanics could be of two types, absolute and convective. Namely, that you create Zakharov spectrum, and then you create some perturbation. What could be is that the perturbation starts off growing like everywhere. This absolute instability practically never happens. The conditions for it are kind of unphysical. I don't know of any physical situation. Well, there is another situation, which means that it's a cascade going on, right? So your perturbation would eventually propagate. It propagates and grows, which again is related to the fact whether your nonlinearity increases along the cascade, etc. Nobody really explored it much, but this would be convective instability. Means that if you have a source and source fluctuating, then your fluctuation would increase down the cascade and eventually will destroy your spectrum somewhere, right? When you go far away. Okay? But on the other hand, what you can do, you can take Rayleigh genes, linearize with respect to it, and assume that you have a small forcing which adds a little bit of it. Then you would have a solution which would be of that type. It would be 1 plus small correction, and this correction is stationary.
Probably stop, no?
So I have a question about the hybrid solution. So when you get to the thermal equilibrium portion, how can you have a constant flux? Because you showed the flux.
Oh, it's there. It's just invisible. In a sense, it's very small because eventually, if you look here, this parameter is just kind of goes to zero. So your flux is constant, right? Because you it's